tuning fork. So the tuning fork itself is 2 tines. It's a piezo element enclosed with metal electrodes. We vibrate it either internally or externally. So due to its high Q factor, it gives a very strong response in the resonance frequency, and it's very good then to use it for AFM feedback. We attach the tip or different type of probes, AFM probes, NSOM probes, thermal probes, and different other probes to the tuning fork rigidly, and that will be part of the tuning. And then this will be used, in fact there is no optics, just this small piece will be used for AFM feedback. Okay, could be in amplitude feedback mode or in phase feedback mode. So you can just move it, and if you look to this side, you will be able to see the cantilever, and if your eyes is strong enough, you can see even the bend of the tip. So the tip is
young, you can see it.
So it looks like this, in fact. Okay, so this is the cantilever and then bent area. So tuning fork in this case will be working in normal force. You know, when people don't like tuning fork because it works in shear force. Shear force means that the tuning fork is this way, and then you have a straight probe, and moving the vibration mode is in this way. While your topography is in z-axis, so you don't want to have a shear force, because then you can easily break that in. So then this solution is really nice using a bent probes. So where it can bend with this cantilever up and down, give it enough flexibility without breaking the probes. So it could be glass probes, or it could be NSOM probes, or it could be either silicon probes attached to this tuning fork. So they can host different type of probes for different AFM or SPM applications. Okay, so we're going to excite the tuning fork externally. So on the AFM head, in fact, this is the part. This is the AFM head together with the sample scanning system. So in this system we have 2 AFM heads, okay? Right tower and the left tower. Every one of these towers also include a tip scanning stage. So in general you have one sample stage, one to move the sample in X, Y, and Z, and additional piezo for the first tip in X, Y, and Z, and the same for the second station. So you could do up to 100 microns in X, Y, Z for the lower one. Notice also Z. Due to the flat structure of the 4 piezo elements, you can do up to 100 microns. Normally, most of the AFM system uses between 5 to 20 microns. So it's good for rough surfaces, for cells, for for like fibers, textile fibers. Or wood fibers, plastic fibers, that would be good to cover with AFM such roughnesses.
So the AFM with the laser deflection, where is the laser?
There is no laser deflection here.
Okay.
It's using the tuning fork for the feedback. Okay.
Yeah, okay.
So in laser
I thought
deflection,
you had it integrated.
no, not
as
here.
well.
Not
Okay. Yeah.
in principle, you could add it. You could have an optical module here to add it here. You would have the beam coming through the objective and reflected back to the photo detector, which also will sit here in an intermediate module between these 2 components. Okay? So you could have a separate AFM. Thank you. So you could have an AFM system working in optical feedback, an AFM system working with tuning fork, and you could have a system working with tuning fork, and it's still possible to use optical feedback as well. Okay. Yeah, so this system is, we're going to do a basic AFM operation, okay, just to see the standard operation of the system. But this system, in fact, is capable to do multiprobe operation. The previous experiment which we were doing is bringing one probe to feedback, delivering the line into the surface, and then bringing the second probe in close proximity to that, and scanning, starting from this point, from the first probe point, collecting the topography and collecting the near field optical signal. Now the signal, one fiber probe. Now before we go to the AFM, so let's see this. So this will be the NSOM fiber probe, in fact. So one probe will be, this side will be connected to the laser. So you will have a very small light source coming out from this position. You can use it for NSOM measurements for high resolution optical imaging, or for optical nano manipulation or activating a specific location for the sample. Could be 50 nanometers, 100 up to microns. Okay? So this will be delivering the light. A similar AFM probe will be mounted on the second tower, the second AFM system. The light, the second probe will come close to the first one, collect the near field light, coupled through the fiber. The fiber is connected to a detector. Could be PMT, it could be an APD detector. Okay? So this will be near field injection of light and near field collection with two NSOM fiber probes, where you can easily use two piezo stages, two AFM independent systems to bring them close enough to each other and to do this task.
How close do you typically get the NSOM probe?
Touching. Yes, because when they are in feedback with the sample, so you have a Z feedback level which you can easily see and monitor with the system. So when you bring them, when you offset the tip, you will see that the Z feedback start to change. They start to feel each other. So you know that this is the point where they are touching each other. So it's so this is what we were doing till now in the morning. In fact, I think we still have one picture like that. Yeah. So this was the AFM, and this was the NSOM image on top of a dual strip. Sorry to shift to the other subject. See these lines here. This is where we were touching with the first step. Right. So we know this is the 0 point, and then from there, and we scan back from the the fixed tip or the illumination. So this is an AFM, this is an NSOM.
But that's AFM with the NSOM probe.
Yes, that is true. It's an NSOM with an AFM probe, and this is the NSOM which is detected there. The NSOM, the optical signal is detected, it's connected directly to an APD, or it could be connected to any spectrometer. In fact, you could do spectroscopy, or you could connect it to the DCSP. Then you do lifetime measurements with these APDs. I think we're still using the same APD. Because the NSOM signal from the instrument, from the AFM perspective, it's an AFM tip.
Yeah.
It will give you topography images, and you take the signal from the detector and you couple it to an auxiliary input here. So it will be synchronized with the AFM. So you could in fact you could couple another signals like electrical signals or thermal analog signals to the system, and you could choose up to 16 channels and monitor these simultaneously.
Okay.
So synchronized pixel by pixel. Okay, so we're going to mount an AFM probe. We just put the sample on top there, no need for vacuum or no need for fixing, just gravity. We put the tip in there. We check the resonance frequency first. There's an automatic procedure to do that, but we can do it also manually. We're going to work in, I think the resonance frequency is about 40. Okay, so this is the peak at the resonance frequency. Normally, the pure tuning fork gives a resonance frequency at 31 kilohertz. And when you add the tip and add the glue, you change the mass and the balance between the two times, so it becomes slightly different. Okay, so we're going to work in phase feedback mode. With tuning fork, this is the good thing, which is not possible in fact with with optical beam down system. You directly have a frequency modulation. In optical feedback system, you work in amplitude feedback. Here you could work with amplitude or with phase. The advantage of working with phase, phase changes are much faster than amplitude changes, especially with the high Q factor of the tuning fork of a few thousands. Okay. Now, but additionally, when you work with the phase, you keep the amplitude not changing, because the amplitude is about few nanometers in that case above the surface. So the phase changes before the amplitude start to change. Okay? So any change of the amplitude during the measurement gives us, in fact, gives us an information about mechanical properties. Okay? So you scan with phase, you get the error signal, you get the high topography information, but the amplitude channel gives you additional information about mechanical properties of the sample. So you don't need to do any force measurements like AFM does, like you do a force measurement, force distance measurement at every point. Here you have only, you're monitoring only the amplitude, and it will give you a nice representation for the elasticity of the mechanical properties of the sample. So that's additional advantage of tuning. So then we shift to phase. Okay, and we select the zero value here, which is the resonance frequency. And then when we're ready to approach, we just put the tip in the correct place above the surface, and we'll be ready to go. So I move the tip in. There is a rough motion first, so we slide it out to put it in the, like in case of we have two probes. Okay. So before starting approaching, let's see some optics here. So we, as I said initially, this system was designed to be integrated with optics. So we have a clear optical axis from top and from bottom, so where one can see the exact contact point of the tip with the sample. Now this is due to the flat scanning stages from top and bottom for the sample stages and the tip stages, and also for the probes themselves. So we will soon see the tip itself. It's made of glass, pulled under heat to form a very sharp end, and then it's bent. So the bend gives, it's about few tens of microns between the cantilever and the end of the tip. So when you are focused with 50x objective on the tip, you don't see any obscuration due to the cantilever. Also the bent angle give it to be exposed, so you can easily see the tip touching the surface from top. Now this is you could see in many systems from below, but only few systems can give you a nice or clear optical axis from top. And that is very important because most of the samples for AFM are opaque. So that it's very important. So that's why people use, for example, side view, but still not effective. If you work with optics, you better work, in orthogonal directions, and not in the angle. So now we're starting from the 10x objective. So we see with the CCD here, you see the upper tine of the tuning fork. If we go down, it's the lower tine. If we go down with the focus mode, we'll be seeing the cantilever. Okay, so this is the cantilever. If we go down, you'll see the end point of the tip. This is with 10x object. Okay, so we switch down with the focus. You'll be able to see the sample. So this is the sample. So we'll be going down. So let's approach the tip. Not directly to the surface, but slightly before, like a few microns above the surface, and then when we switch to 50x objective, so we'll have better field of view, and we'll see the advantage of these exposed tips when they're touching the surface. So the tip is coming down now. It's the approach process is done with with a Z stepper motor, and this is linked also to the Z piezo. So we ensure that the engagement with the sample is done in a gentle fashion.